Yeah, just before the intermission, I was drawing the phase diagram of yttria stabilized zirconia, and I had said that this is the loading amount, that this particular diagram is a loading amount, and at about 2 or 3 mole percent I get the maximum toughening. Uh, Now, let us look at why over here with calcia and magnesia I require higher amounts. This is the phase diagram of calcia oxide zirconium dioxide. You will see over here, look at the change in the scale. This is entirely different from what I had drawn over here. There is a large scale change in scale. So, the cubic stabilized zone is over here, which my zone of interest, tetragonal stabilized area, is up to here, which is about 8 mole percent, and this is why over here it went up like this. This is the amount of calcium oxide which is required is much more higher. So, my zone of interest is up to here because this is the zone I intend to use. So, that I have got only tetragonal phases which will cause the transformation toughening due to conversion of tetragonal to monoclinic phase. When I use magnesia, with magnesia my area of interest is up to here, because this is my zone of interest. I am not interested in monoclinic tetragonal. This is my zone of interest, and hence with magnesia I require a larger amount of magnesia to have to work within the tetragonal partially stabilized zirconia, where most of the grains are tetragonally stabilized. Now, this is the reason why we have different amounts of magnesia or calcia or yttria which are to be added for fracture toughness. One of the biggest problems of this transformation toughening is what we call aging. Like say jet aircrafts which use duraluminum, that is aluminium which has been toughened with copper, which forms Cu3Al precipitates, which helps in making the aluminium tough, so tough that it can be used as the outer body of an aircraft. One of the problems of these is with time, that is especially as the number of flying hours increase, the strength of the duraluminum body decreases. We have a similar problem with transformation toughened zirconia also. The limitations are that over time with use, the tetragonal phase slowly transforms to the monoclinic phase. That is one part. The other part is, in each of these cases, whether it was magnesia stabilized or calcium stabilized or yttria stabilized. The tetragonal phase is stable above a certain temperature. In yttria, it is up to about 900. That is, above 900, it is a tetragonal phase which is stable when I am using yttria stabilized zirconia. With calcium stabilized zirconia, it is around 1100 degrees centigrade, above which tetragonal phase is stable. With magnesia, it is about again 1100 degrees centigrade, above which the tetragonal phase is stable. So, obviously, no toughening action will be there above these temperatures. That is, above 1100 degrees centigrade, tetragonal phase is stable. So, the temperature range over which this material really works as a transformation toughened ceramic is room temperature to about 1000 degrees centigrade. That has to be the first thing that you will have to remember. That is, it is not that you can operate at high enough temperature. So, in a cutting tool system where I am using zirconia as a cutting tool, I will also have to use coolants to ensure that the temperature at the tip of the cutting tool, that is the temperature at the tip of the cutting tool, does not exceed about 1000 degrees centigrade, because above it the tetragonal phase is completely stable and there is no question of tetragonal to monoclinic transformation. It is only below 1000 degrees centigrade or so do I have tetragonal to monoclinic transformation. So, frequently what we have to do is that we have to add coolants sprayed on workpiece. At times we may require at very high cutting speeds. We may have to use even liquid nitrogen to cool the whole thing to ensure that the temperature at the tip does not go above 1000 degrees centigrade. And so, this requires a balance of what the phase transformation temperature of the margin steel is, if there is a phase transformation on being cooled, because you cannot allow the temperature, the cutting tip of the partially stabilized zirconia to exceed 1000 or 1050 degrees centigrade. As I said, these partially stabilized zirconias are also prone to thermal aging. Let us look at a diagram. This is a percentage tetragonal phase and temperature is over here. Let us say this is 600. Now, let us say I am heating it up This is increasing temperature. When I am cooling it, I may jolly well see a situation where I see a hysteresis. That is, during the cooling curve, after heated it up to here, I have got tetragonal stabilized zirconia. I am cooling it during this period temperature where it is the tetragonal phase is retained, and as I am cooling down only after here the monoclinic phase comes up here. So, this is the tetragonal phase, this is 0, this is a monoclinic solid solution. So, here I have this major aging problem, that is I do not have, I have a delay, I have hysteresis in the increasing and decreasing temperature of the cooling curve. Frequently what we do see is, if I draw a diagram of say MOR, MOR means modulus of rupture versus temperature. If I have this modulus of rupture, this is the range for magnesia stabilized ZrO2. Whereas, if I am using yttria this is the range for yttria stabilized zirconia, and frequently what we do see is, because we have got a higher modulus of rupture with yttria stabilized zirconia, most of the materials which are used for transformation toughening of zirconia are basically yttria based. It is due to these two reasons over here, because with yttria stabilized zirconia I have got a higher modulus of rupture than magnesia stabilized zirconia. With yttria stabilized zirconia, this hysteresis loop is much smaller, and aging effects of yttria stabilized zirconia are far lower. I have talked of here zirconia is the matrix where I have added yttria, calcia or magnesia to cause formation of tetragonal solid solution, which are basically oblate oblate shaped materials. However, there are other materials like say alumina. Here zirconia has been added to strengthen the material. The amount of tetragonal ZrO2 at room temperature and the fracture toughness. In alumina, 15% zirconia additive is added, tetragonal content is 20%, and the fracture toughness, of course, I should put a unit. Fracture toughness is of the matrix, of course, is 9.6. In alumina, there have been reports of, let us say, 30 mole percent zirconia containing 2 mole percent yttria. Tetragonal zirconia is 100% and the fracture toughness is very high. Zirconia has been used as an additive in spinel to the extent, say, 18% of zirconia added. Tetragonal zirconia formation was 50% and the fracture toughness was just 4.6. It has been used in mullite matrix also, about 23%. The percentage of tetragonal zirconia is 30% and the strength is about 4.5. All of these values are higher, much higher than the matrix itself. So, zirconia is been used as a particulate reinforcement in other matrices like Anuvilla, Spinel, Mullite. Let me remember if I, let me see, silicon nitride, Si3 and 4, 15%, 30%, and this was not TSS, this was cubic zirconia which was formed, and the strength fracture toughness was 8.2. Now, you better remember this is cubic and not tetragonal. I will leave it to you to find out why did this happen. Why did this happen? Let me put in another unit which is the strength of matrix in, say, megapascal. This would be 480 for 15% zirconia additive. This one would be around 1200 megapascal. For the spinel, it would be 500 megapascal. For the mullite, it should be around 400 megapascal. And in silicon nitride, it will be around 940 megapascal. So, what we see is here that we have this zirconia reinforcements causing strengthening of the matrix. Yep. So, I would not elaborate any more on this. I have given you references to books where you can find chapters on transformation toughening. There is one more toughening that I would like to focus on now. I had referred to it in passing in the past, and those are glass ceramics. I had talked of during my introduction phases when I showed you the coralware, and I have talked of it in various cases because that's a very important piece of technology. The reason being is that a glass is a non-porous body. If I can load it heavily with ceramic particles, and more so if I can generate it from the glass phase itself, that is, I do not add anything, I do not add much, then I should be able to have a very dense glass. Now, one of the things that experiments that I do in the laboratory is I take silica about say 70 weight percent, Li2CO3 around 28 weight percent, 28, 29, and I take titanium dioxide at times, which is about 1%. Let us forget about titania. Let us say we have got SiO2 70% and Li2CO3 30%. I take this mixture and melt it. Let us say a good temperature to melt would be around 1350 degrees centigrade, which allows the glass to completely form, no bubbles, etc. I keep it there for a period of around 6 hours, so that all the glass has melted, and then I cast it in a brass mold. Here I get a clear glass. What I do in the laboratory when I am teaching is this, that I take this clear glass and heat it to a temperature of around 450 degrees centigrade. The times that I will keep is varying. I'll vary the time, I'll tell you why later. And then finally heat it around 750 degrees centigrade. When I get a glass which is whitish, totally. Now, let me look at this temperature, 450 degrees centigrade. Let me pick a time, 2 hours. 750 degrees centigrade, let me pick a time, 6 hours. 450 degrees centigrade, 8 hours. 750 degrees centigrade, let me keep it 6 hours fixed. So, I have got this product and this product. The difference between A and B is that A had been heated at 450 degrees centigrade for 2 hours only, while B has been heated at 450 degrees centigrade for 8 hours. Both have been subsequently heated at 750 for 6 hours. After this, if I polish, etch, and look at it under a scanning electron microscope, what will I see? In this particular case, A, what I will see is very small tiny crystals whose dimensions may be about 10 to 20 micrometers. In this particular case, what would I see? In case of B, very fine dispersion in matrix. Now I bring in another constraint. Let me heat it only for 1 hour at 450 degrees centigrade, and let me keep this 6 hours constant, and let me label this C. In C case, what would I see is very large grains. They can be, as I have seen, grains as large as 500 micrometers across. So, what is happening? Why this temperature is kept constant? So, why are the sizes varying? The simple reason is, if you look at Li2CO3 SiO2 phase diagram, you will see that over there there is a phase separation occurring. At 450 degrees centigrade, when I am heating, that is after I have made the glass, quenched it, means cooled it very fast, I have got this clear glass. When this clear glass is being heated, if I heat it at 450 degrees centigrade for a very large length of time, what will I have? I will have a large number of nuclei forming. And as a result, when I am subsequently processing at 750 degrees centigrade, these nuclei will grow only into slightly larger grains. Whereas at 1 hour, what would I get? Hardly a few nuclei. So, when I am processing it at 750 degrees centigrade, around these very few nuclei, crystals can grow in, and they can become very large. They can become very large. So, if I have got heavily nucleated crystals as in B, I will have a very fine dispersion of crystals in the matrix. But if I have very low nucleation, by controlling the nucleation time for only 1 hour and then I process it for 6 hours at 750, I will get very, very large crystals. Uh, these crystals, this type of very large crystals are used for decorative glassware, where the color of the glass changes depending on your angle. But this very fine dispersions in a matrix gives you dispersion strengthened glasses. And this is the fundamentals basically of glass ceramics. I do not have the time and space to take up the individual phase diagram, take up the individual three-phase diagrams to illustrate the point as to how in such systems we can have a glass ceramic. However, the three-phase diagrams of say SiO2, lithium carbonate, lithium oxide, which is derived from lithium carbonate, titanium dioxide are there. You can look up that, you can then realize what is the crystallization, what is the crystal that is happening, and how to generate these two structures. By varying the amount of further additives, these very decorative glass pieces can be made, in fact they are made, while very strengthened glass ceramics, say like which are used in coral dinnerware where they require fine dispersions, these can be made. I have to leave it, the glass ceramics part here, because I have dwelt on it on many occasions. Now, before I wrap this transformation toughening up, I am going to look at another possibility where vapor phase processing can be used for strengthening of ceramics. Like say silicon carbide boron nitride. It can be also silicon nitride. You see, these are materials which are being used heavily in space and yes, in missile technology also. In such cases, there is having one species deposit another, like the silicon carbide, boron nitride, silicon nitride, or it can be silicon carbide, boron carbide, silicon nitride, all of this. This requires vapor phase processing, and over here the pyrolysis routes are the basically polymer precursor pyrolysis. To take an example of polymer precursor pyrolysis, what we can do is, for example, we can take the case of say I have to explain how do I cross link. This I had said earlier. That is, during chemical vapor infiltration technique, I had said that I can prepare silicon carbide by pyrolyzing silicon tetrachloride with silicon with methane. Like say, what we can do is we can have silicon which on pyrolysis will give me so we can get silicon nitride from polysilyl carbodiamide. If what we can do is, if I want this complex structure, say Si, boron, carbon, nitrogen, ceramics, if I want to do it, what would I have to do? I would have to do something we have to synthesize first this sort of a molecule which has got silicon, carbon and boron. This on pyrolysis would give me a structure like this sort of a structure, which has got both silicon, nitrogen, carbon, boron. This on further pyrolysis would give me plain silicon, boron, nitrogen carbide. Now, these types of materials are really now coming into play, not as a composite. Please understand, this is not a composite, it is the same molecule which has got all the four, the silicon, carbon, nitrogen and boron. And hence, in this particular case, we have a real strengthening of whether you call this a silicon nitride matrix or a silicon carbide matrix. It depends, it's a mixture of both, with another one with a boron carbide or boron nitride, what I had written earlier, through the precursor derived polymer ceramics route. Now, I bring this in because this is not a standard topic you will find in any book, but this is what is going to be the high temperature, high strength material of the future, which will be used extensively in space, in aerospace, even in high speed trains and personal armors against any hostile attack. So, polymer precursor derived ceramics, where we have layers like silicon carbide, boron carbide, silicon nitride ceramics. They fundamentally, as a polymer, had the organic components of these three arranged as I have shown you here. So, in this particular one, while the thermodynamics, the pyrolysis rate, everything has to be very rigorously controlled, yet unlike the other systems I have talked of so far, I have got a mixed ceramic composite system which is mixed at the molecular level itself. I am not talking of particulate levels anymore. And as a result, these polymer precursor derived ceramics have possessed very high mechanical and thermal properties, which is far above the whatever you have today. So, basically, if I have to do this, what do I have to do? I have to synthesize the basic organic molecules, condense to form the polymer, cross-link wherever required, so that I have got a polymer monolith, and then I merely thermolyze or basically carbonize, or better word is not carbonize, better word is decompose in inert atmosphere to give me the ceramic monolith of or anything. It can be SiC, boron nitride, silicon nitride. It all depends on what the starting organic materials are. As I said, because this is mixed at the molecular level, the strength of these materials is phenomenally high. Oh, Si 3 and 4 is phenomenally high and much above the material, the strength of most of the ceramics I have talked so far. To summarize, this chapter has got 3 sections: transformation toughening. I have talked of particulate toughening. I have talked of reaction or chemical vapor infiltration toughening. I have talked of toughening caused by microstructure or phase change, as in the case of yttrium-stabilized zirconia. I have talked of glass ceramics, and finally, I have talked of polymeric precursor derived ceramics, which allows us to mix at the molecular level the various systems, so that we have got a very high, very strong composite. Having spent 3 hours on this lecture, what I would say is the biggest problems of ceramics is, unless you have standardized the starting materials and the processing conditions very well, so that they are perfectly repeatable, things which are not tough to do. But once you have determined that this is the processing condition under which I get an almost dense, 100% dense material, once that can be done, a lot of very toughened ceramics can be generated. You see, today we have, say there, I won't name the company, but there is a company which sells gas burners. You have got gas burners at your house whose burning heads are made of metal, brass, with holes in it, 2 or 3 millimeter holes in it. The problem is the burning efficiency there is only 15%. So 85% of the gas from the cylinder is wasted, and you are using only 15% of it. But there are companies which have come out who have got porous ceramics as the burning head. One of the first things that will be required for that porous ceramic is, in addition to being thermally shock resistant, is that what you will need is it be abrasion resistant, it be mechanically hard, and also be resistant to sudden shocks. It is very common in households that they take the top off to clean and suddenly it pops off onto the floor. If there is a pretty high strength material which is required to prevent it from breaking, just drop your cup from your hand, it will fall on the floor and crash. You do not want your ceramic burner head to crack up if it falls on the floor due to while cleaning. So even there we require very high strength ceramics that are immune to thermal shock and also mechanical shocks. The list can go on. It can be expanded to anywhere, and today it truly is being expanded to many different areas. Hence, toughening, people are exploring toughening mechanism of ceramics by, for example, in coral dinnerware, by layering. I had talked of layering 2 classes ago, if I remember right. They will make different the coating layers of different thermal expansion coefficients, so that the outer layer imposes a compressive stress on the lower layer, the lower layer imposes a compressive stress on the still lower layer, and that is how the whole material is strengthened. In fact, today with availability of a lot of facilities, toughening is something that is being done even, say, in 1/4 the size of the room I am lecturing in, which I guess is 20 by 30 room. So in a 10 feet by 10 feet room, people are setting up processes, furnaces to toughen ceramics, so that it can be used for various purposes. Please understand, many of you fly the runways. Do you know how tough, what is the material for making the runways? If it's in the runways where the large Boeing aircrafts can come in or fighters which drop in, the material that is used in the runways are silicon nitride, because they are so hard. The impact needs very hard materials. The stone chips used for making the roads is not the top surface material while making the runways. They are very, very hard ceramics. It would be far better if one day we can use transformation toughened ceramics over there, so that we could increase the lifetime of the runways, because the more and more high performance aircrafts are coming in and we need higher and better, stronger runways. Thank you.